We're going to take a look in Chapter 10 today at the last three sections, 10.8, 10.9, and 10.10. And we're going to start with the quality versus the quantity of energy. And when we use energy to do work, we do what we call degrading the energy. We degrade its usefulness. And this does not conflict with the first law of thermodynamics, which says that energy cannot be created or destroyed, only changed in form, because we're not creating or destroying, but when it goes through the process of being used, it degrades it and it's not able to be used the way it was before. An example would be putting gasoline in your car. That's a form of concentrated energy, and this is energy that's used to do work. Well, once you use that concentrated energy in the form of gasoline to do work, to power your car, and there's other things that happen, like it gives off heat and heat transfer to the atmosphere and to the engine itself and things like that. And there's some pollutants that are given off. This energy can no longer be used again in this way, and it leads to what we call energy spread. The next section is going to cover fossil fuels. Fossil fuels are carbon-based molecules that form from decomposing plants and animals, and we use those as a source of energy in the United States. And this is a cool graph just showing how we have used wood, coal, petroleum, natural gas, and then the introduction of hydro and nuclear power between 1850 and the year 2000. You notice there's quite a bit of changes in the usage of those different energy sources. And right now, our fossil fuels, our coal and petroleum and natural gas, make up a rather large portion of the fuels that we use, the sources of fuels that we use in the United States. Petroleum is a thick liquid and is made up of many hydrocarbons. We've talked about hydrocarbons before in chemistry class. Those are compounds composed of the two elements carbon and hydrogen. And this is the whole area of organics that we don't get into in high school chemistry, but you will have the opportunity to do in college chemistry. So if we look at petroleum, they're rather large atoms or molecules made of strings of carbon atoms and chains of carbon atoms. So gasoline itself has between 5 carbons and 10 carbons per molecule. Kerosene and jet fuel, 10 to 18 of just carbon. Diesel and heating oil, lubricating oil is 15 to 25 per molecule is what we're talking about. So you stop and think about water being H2O. Well, diesel fuel or heating oil and lubricating oil for your car can have between 15 and 25 carbon atoms alone in just one molecule. And asphalt has even more than that, more than 25. If we look at natural gas, on the other hand, just some of the smaller compounds that we use, methane is CH4, ethane is C2H6, propane, butane, pentane, hexane, heptane, octane. These all sound familiar to you. I know that they do. We've used some of them in class before. So those are natural gases that are made up of hydrocarbons, not quite the large chains that we looked at in the last example, though. Coal is another hydrocarbon, but it's made up of mostly carbon, very little hydrogen. And this is formed from the remains of plants under high pressure and heat over time. And if you notice in the first example, lignite, for example, there are 71% mass by composition of carbon atoms in this type of coal and only 4% hydrogen. 23% oxygen, 1% nitrogen, 1% sulfur. So you notice that while these do have some hydrogen in them, these forms of coal that we're looking at are a huge majority of that is just carbon alone. The next concept that we're going to look at is called the greenhouse effect, and this is one that you should be familiar with. I think it gets covered in elementary some, and this is also a concept that we're going to touch on again in biology class. So the greenhouse effect, a greenhouse's job is to trap heat and to allow light to come in and trap some heat in there so that the plants stay warm. And if you look here, they show the Earth's atmosphere on this drawing. And this our atmosphere is very important to us as far as a blanket to keep warmth in, to keep rays that come in, keep some of that heat trapped so that we don't go extremely cold or freeze. The planet freeze at night when the sun's on the other side of the earth. So this blanket is made up of carbon dioxide, and that carbon dioxide helps the heat rays to not leave and not leave in huge quantity. So it traps it and keeps us warmer. Now that doesn't mean we don't get cold. You know that it's wintertime and we have nights that can be below zero, and there's places on the planet that are extremely cold. But that layer of carbon dioxide around the Earth's atmosphere, in the Earth's atmosphere, actually is what keeps us warm. Now, there are some questions that arise because of this. Due to the burning of fossil fuels, this layer of carbon dioxide that allows us to stay warm, scientists are concerned that has become too thick and doesn't allow enough of the heat and radiation to escape, trapping it next to the Earth, and they're concerned that that could lead to global warming eventually. But the greenhouse effect is one that you need to know, and it exists. It's not that it doesn't exist, it's just that does it lead to global warming? That's where there's no definitive answer. This is a graph your book includes that deals with exactly that, with global warming issue, and is suggesting that over the last 1,000 years that we have significantly increased the amount of carbon dioxide in the atmosphere, and that's measured in parts per million. They have 250 up to 350, and if you notice how it looks like it stayed pretty level for quite a while, and as we start to burn fossil fuels and more people on the planet are using more of those fossil fuels, that carbon dioxide level would increase this much. The atmospheric carbon dioxide is controlled by the water cycle and is thought to be able to raise the temperature of the globe by about 10 degrees Celsius. Again, that's not something that's been backed up by scientific data. So we have new sources of energy that we need to look into. In order to get away from using all the fossil fuels and causing the possible atmospheric problems that the scientists are concerned with. So solar energy is one that we see used more and more with solar panels. Nuclear energy can be questionable at times because of the danger of meltdowns and things, but it's relatively safe and is very, very efficient and effective. Biomass is an energy source to be using biomass as a fuel. Wind energy with windmills, and then synthetic fuels that are being made is another source also. And if you go to Mineral Area College, they have a whole division that actually deals with these alternate energy sources for this area. This next section is going to finish up the chapter, and it's energy as a driving force. And this says natural processes occur in the direction that leads to an increase in the disorder of the universe. So the example is this ideal gas that's under a pressure at a certain volume right here and a vacuum on the other side. So what happens when the valve is open? You're going to have gas released from one side into the other side. This is an example of matter spread. Matter spread is what happens when molecules of a substance are spread out and they occupy a larger volume. And that's what happens in this case. There are two driving forces that they think drive us to move energy from one area to another, and it's called energy spread and matter spread. Let's look at energy spread. Energy spread in a given process, concentrated energy gets dispersed widely, and this usually is a very exothermic process. So we have energy spread here where we have energy being given off and dispersed in a very quick method. Matter spread is when molecules spread out to occupy a larger volume. The processes are favored if they involve energy and matter spread. It will help drive a reaction. So let's look at entropy. Don't confuse this with enthalpy, which is what Hess's law dealt with. This is entropy, and we're going to signify it by using a capital S. And it's the function that keeps track of the tendency for components of the universe to become disordered or disorganized. And this shows order within a solid, such as ice in this case, and the order and the structure that's there. And then what happens when gas is at that is heated up to a gaseous state is in the form of steam, and it goes crazy bouncing around, and there's really no rhyme or reason or order to it. The measure of disorder or randomness is what entropy is. So what happens to disorder as energy and matter spread? Well, as energy spread happens, faster random motions of the molecules happen in the surroundings. As matter spread happens, the components of matter are dispersed and they occupy a larger volume. So we have faster, more random motions at a larger volume, which is going just to lead to disorder. The second law of thermodynamics states that the entropy of the universe is always increasing. It's always leading toward disorder. So you need to know the first law of thermodynamics and the second law of thermodynamics for the test.